All right, hello out there. First, it wouldn't let me in there a couple times. Like, what's going on here? So look, I think I'm in there now. So, anybody hear me? Or
Yes.
that's tremendous. That's good news. All right, so let me bring up files we need for today. And I'll get the screen share going here in just a second. You're not missing anything exciting. All right, so should be, I believe the plan will be the next two sections here in chapter 4, the 4.4 and the 4.5. All right. And let's get that going now. And hopefully we are looking at 4.4, the Bayes theorem. Okay. Now the Bayes theorem is going to be sort of it has to tie in with what we did last week on the conditional probability. If you had not viewed that video, you might be a little confused, or if you attended the class, either way or whatever. So expect it to be a little confusing, but in a nutshell here, Bayes theorem can be used to, let me jump down here to a probability tree here. I'll skip past the formula for a minute. We'll come back to this kind of stuff, but see, like last week, we learned that anything on the second branch of a tree was conditional. Like this one is a probability of red given that it came from B1. Well, what we're going to learn today with the same kind of tree is what's the probability of B1 given that red was known. It's the reverse. So we have a little formula for that. And let's come back up here. Now, I'll kind of show you you can kind of sort of work through it without getting too bogged down on the formula itself. And I think it's important, obviously, to look at the formula and go through it, but I'll try to explain it in a way that, kind of takes a little bit of the formula part out of it here. Now, conditional, which we looked at these ideas last week. And we had, anytime you do a conditional, like so in this case, it's the probability of B given A, it's always going to be the intersection, the and between them. And in the denominator is always what's on the right of the conditional. So P of B given A is going to put P of A in the bottom, whereas over here, P of A given B is going to put P of B on the bottom. The numerator would be exactly the same because if the two events are A and B, the numerator is always the and between those two or whatever. So now to come up with this Bayes formula, what they've done is they've taken this situation on the right, and if you, let's see, do a little simple algebra here, you don't have to actually do it, but if you were just solving for the P, A, and B part right here, you'd bring the P of B up and over to the other side. So then, in other words, we can say that, I'll write it right here, then I'll kind of get rid of it because it'll look kind of messy, but so I'll use a different color. P of A, and that way you just at least be able to see it whenever you see the formula, times P of B equals P of A and B. So it's basically this P of B brought up to the left side. Then they took on the formula on the left. Actually, I might have this. I have this. I'm sorry. Yeah, I got it going. Well, what I was writing was true, but it's not matching the formula right here. The substitution goes the other way. They're taking the one on the one on the left and substituting into the right. Could have been done either way, but I want to make sure it matches the formula that I have written there. So if you take the number 1 up there, you then have this. And then on the formula number 2, P, A, and B right here is then just replaced with this. Now they have the other order. That makes no difference whatsoever. But this multiplication is commutative mathematics. It's the order doesn't matter. So P of A given B can also be expressed as P of A times P of B given A divided by P of B. So it's just kind of combining those two formulas and working with this result. So, okay. And you're not worried, about having to solve that yourself or anything. I just kind of want to show you where that came from. Okay. Now this, of course, can expand for 2 or more cases here. So they're saying then that we've done that before, where the total comes from the different branches of the tree. So P of A can be P of A given B1 times P of B1, and then P of A given B2 times P of B2, so forth, so on, to how many events you actually have here. All right. Now this is kind of the formula now expanded to if we just have two outcomes. And then the 3 or more outcomes is going to use basically this result up here. So they're taking that formula we already have right up here, and now we're expanding that out a little bit. So, all right. So if you have 2 outcomes, the first branch is either going to be B, it's going to be A or not A. So P of A times P of B given A plus P of not A times B given not A. All right. Now, 3 or more cases, the denominator keeps expanding here. Now then, of course, 3 or more cases, now they're using this as an A1. So I'll say you had like an A1, A2, A3, and you're finding out A1 given B. You would have this denominator. So you'd have everything. Now let me show you. I'll mark it right here in the formula. So the key on this is the denominator is going to be calculated the same way every time. It's just the numerator is going to be different. So let's say if this is, so I don't have to rewrite the whole thing, but let's say this was 3 events and it was P of A2 given B. The denominator would be exactly the same because the denominator has to include every way you can get to B. In this case, it's A1, A2, A3. Every way that gets to B is on the bottom. The numerator then, that's the only thing that changes here is the numerator. Everywhere we see an A1 comes an A2. This is a little confusing to grasp the idea just by looking at these formulas. I realize that. And so let's make some use out of this with some examples, and not only here, but then in the My Math Lab homework, because it's kind of the formulas here can be a little overwhelming. But I think if you see how it acts, it might not be as bad, at least anyway. Okay. I probably found that problem somewhere. Google search some examples. I don't think it came from this book per se. Not that it needed to. Okay. So we've got a box contains 4 red balls and 2 green balls. Second box has 4 green and 2 reds. By design, the probability of selecting a box 1 or box 2 at random, or 1/3 for box 1 and 2/3 for box 2. Don't worry about how those probabilities came about. You just have to go with them. Now, the probabilities for the red and green balls, we'll figure those out ourselves. Yeah, I don't know why it's not equal for each one, but that's okay. Maybe there's 3 boxes there and 2 of them are box 2s or something, and, well, whatever. I don't want to get bogged down on that. So, okay. So what's going to happen here is we've got 3, we got box 1, box 2, and then we've got red and green. All right. So the key is getting the tree done in the correct order. So this would have to start out first, which box did it come from? And then color from the box. So the tricky part sometimes is getting the tree in the correct order here. Now let's see how I did this. Now the B1 and B2, I just took from the given information, the 1/3 and the 2/3. Now the red and the green. Now notice this is a little bit different than what we did last week with problems where we're taking balls, things. This is not like the replacement problems last week. I remember last week we'd do like, maybe red 1, then red 2 or something like that. This is different than that. So once you get past the box part here, all 6 of the marbles are there. We're not branching any farther than that. So it's not like we've removed a color or anything like that. So there are, what's comprised of box 1? So box 1, well, they didn't label it box 1, but I guess intuitively they should have, but you can just kind of use logic and say, well, the first one you see could be box 1, the second one, box 2. So 4 red and 2 greens. That means it'll be 4 out of 6 chance of red and 2 out of 6 chance for green. And then for box 2 has 4 greens and 2 reds. So it'll be 4 out of 6 green, 2 out of 6 red. And then there's how I got those probabilities for that tree. Now, suppose we wanted to find the probability of B1 given red. So notice now, that's what makes this a Bayes situation, is we're moving forward. We're going to just find the probability of this given a later branch. That's the uniqueness behind this idea. If the question had just said, find the probability of red given that it came from B1, game over, 4 out of 6 right there. But this is not done that way. Now, I wrote it out kind of officially using the formula right here. But what we really need to do, all we have to do is that, the denominator is going to be multiply the paths that lead to red. And so because the bottom is the probability of red. It's always the probability of what's on the right here. So you see B1 goes to red, so you multiply those two together, and then B2 goes to red. So B1 over 3 times 4 over 6, 2 over 3 times 2 over 6. That's going to be on the bottom. Now the top is going to be whatever the question is asking you here. It's asking us B1. So that's the only one we're interested in. So the B1, the numerator B1 times P of R B1 is just those two numbers multiplied together. Now let's come down here and look at the numbers. Okay. So here's P of B times P of R given B1 will just be the 1/3 times the 4/6. Now one thing I can tell you about this is whatever's on the top is always part of the bottom. The bottom is going to be just, but there's other stuff on the bottom. That's the difference. So the top part would just be the B1 times the red, like this, and then I explain what these were going to be: the 1/3 4/6, and then the 2/3 2/6, and then you just calculate that out from there. Like I said, you can kind of do, once you get the hang of this a little bit, you can kind of do it without worrying about writing out the formula or anything like that if you get comfortable with it. And that just happens to end up being 1/2. So you have a probability of 1/2 that it came from box 1 if you know it's red. All right, let's see what we got here. Okay. So we got to kind of, build our skills here up a little bit. And now here's this one saying, given the ball was red. Oh, I didn't put, Oh, there it is. Yeah, there was the question for part A, actually. Yeah, probability. I kind of wrote it down there. Given as red, what's the probability selected from first box? Now, given the ball is red, again, what's the probability that it was selected from the second box? All right. So the denominator is going to be exactly the same. It's going to be that same set of numbers, but the numerator, now we're only concerned with box 2. The numerator is going to be, that one works out to be 1/2 also. So the numerator will be 2/3 times 2/6. B2 times red. Okay. And that one also happens to end up being 1/2, just by coincidence. But it's sort of explaining this down here, a little bit. You don't have to worry too much about it, but it's just a coincidence. But it's because I think, there's more red, even though there's more red in box 1. Box 1 has a lower probability of being chosen. So, and then you have fewer reds in box 2, but a higher chance of being chosen. But it all kind of ends up equaling out in this case to be 1/2, just kind of a coincidence. I could do real quick. Why don't I do, let's see, how many of these examples do I have, before I go to the homework? Let's see. That's good. Okay. I won't do both of them, but I'll do one with the green just to show you the difference here. I'll do that on scratch page, or maybe I'll just squeeze it in here, and not have to. Maybe that way I don't even have to worry about moving to another page, just squeeze it in here, and that way you can see where all the numbers are coming from, or I could just copy the tree, whatever. I'll just do it right here. So let's just suppose what? Who? What? Oh, thought I heard something. So let's just say probability of B1 given green. Now I can write the formula out here. I can do that, or I can just show you by numbers what's going on here. I'll put the numbers in there, and then if you want to see the actual formula thing, I can. Let me do the bottom part first. The bottom part is going to be everything that goes to G. So you see B1 goes to G. 1/3 times 2/6. And then B2 goes to G right there. See that? So B2 to G is 2/3 times 4/6. Like so. And the top, because the question is asking B1 given G, the top will just be B1 and G right there. The top's only going to have one little product there on it there. So B1 and G, it's going to be the 1/3 times 2/6. And let's see what this is. It's 2/18. Oh, I won't worry about reducing it till the end. And then it's 2/18 plus 8/18. So if I'm doing this right, if I'm doing it wrong, then let me know. So I wrote it like that. 2/18, 10/18.
Sorry, Professor. Can everybody mute? We're getting some feedback.
I don't know if it's coming from me. I think, I don't know, somebody's mic might be on or something.
Yeah, it's not you. It's not you.
Yeah, I think somebody's got their mic on.
I think it's Roosevelt.
Yeah, that happens. Yeah, so if you got your mic on, unless you're about to say something, that's one thing. But yeah, I was starting to hear that too. I was about to ask about that. All right, I still hear it.
Hey, Roosevelt, can you mic your phone?
Oh, you see who it is? Okay, I didn't go over there and look. So yeah.
He's got it. Thank you.
Okay, the 18s will cancel. You get 2 over 10. It'll end up being 1 over 5. Reduced or whatever. So you have a 1/5 probability that you chose B1 given that it came from green, given that it was green ball. But you see, I did that without even worrying about actually using. I mean, well, yeah, I was using the formula, but without actually, writing it out per se. All right, let's keep going. We're not done with this yet. Well, we're done with this problem, but let's see. Yeah, just let you know is that if B1 given green, that means B2 given green. If that's 1 over 5, that would have to be 4 over 5 because they would have to add up to 1. The other two were 1/2 and 1/2, so they did, But if I worked out B2 given G, or you could try it yourself, just make sure you got 4 over 5. You don't have to do it because it felt like it. But it would definitely be 4 over 5 without even having to work it out because the only way you're getting to B2 is either red or green. There's no other options. Now, if we expanded this out, that'd be a different story. All right. Screen froze for a minute. Here we go. Okay. All righty. Oh, 3 things going on. This could be exciting. Factories, light bulbs. Got a factory A, factory B, factory C. All righty. So factory A produces 20% of the bulbs. Oh, I think that's a typo. I just copied this from somewhere. I didn't even know. I wonder if I noticed that last semester. Don't remember, but I mean, I think that word right here should be bulbs. Huh? Okay, I didn't even catch that. I don't think. Well, maybe I don't remember. Maybe I did, and I don't remember that I caught it. But yeah, bulbs. So okay. So 20% are coming from A, 50% are coming from B, and 30% are coming from C. Now here they're telling you now once you get past A, B, C, the next thing to determine will be defective or not defective. All right, so it's telling you 2% coming from A. In other words, the probability the bulb is defective is 2% given that it came from A, 1% given that it came from B, and then 3% given that it came from C. Now, let me get the tree constructed, then I'll come back up here and read the actual question. Okay, okay, there you go. That's just my choice. D for defective and then D prime for not defective. Or, which means a good bulb. So did I not draw the tree here? I guess I didn't. Where's my tree for this one? That's weird. I wrote it. I just mentioned we didn't really need a tree because it had everything we need right there. But maybe I should just sketch one just maybe on my scratch page or something. But here's ABC is going to be first. In other words, it's going to look like, I'll just kind of rough one in here, like just so you can at least, okay. All right. So that's A, B, C, and then you got a defective, not defective on these, each one. Now this one's actually only asking for defectives, I think. Let me see if there's any part of this that asks for not defectives. I want to tell you how we'd handle that. So notice it doesn't give you the probabilities for being not defective. It gives you 02, 01, 03. I'm just going to 02, it's giving you these. Didn't give you the others. Well, one thing we learned last week was if you only have 2 branches on a tree, they have to add up to 1. So now it could have asked not defective in the question because it would have expected us to figure that out. So if you got a 2% chance that it's defective, how about a 98% chance it's not defective? and then 99 for this one, and then 97. But the questions were whatever these percentages were, what, 0.2, 0.5? I might be wrong here. Or is it 0.3, 0.5, 0.2, whatever. I got it right in the notes there, but so you can fill out missing information like that, when especially with only 2 branches. If for 3 branches, you better know 2 of them, then you could figure out the third one. You couldn't do it with just one, unless they told you the other ones were equal, but I mean, that's not going to happen. So then you could do it. But I went ahead and just did this one using the formula. Yeah, okay, I was right, 2, 5, but we could do it without it. So I can go back to the tree and show you. So on the bottom, it's going to be everything that leads to defective. A, B, and C all lead to defective. So I'll switch back over here. You see, so A goes to defective. B, so you multiply those two, and then these two in this path. You multiply those. That's on your denominator. And then the numerator is only going to be what is being asked in the question. And it's B. Find the probability of B given D. And then so we only have to choose the middle path. So it would just be those two right there would be the numerator. 0.5 times 0.01. And so there you see there's the ones I pointed out all along the bottom, and there's the one that's on the top. And like I mentioned, whatever's on the top will be one of your components on the bottom for sure. Or other way you look at it, out of all your components on the bottom, one of those will be the numerator. Okay, so I just put this in the calculator and got 0.2778. Always remember, since these are probabilities, they must have a value between 0 and 1. So obviously if I came up with some sort of 1.23, then I messed it up. All right, so let's see what we got here. Let's see what's next. 1% of the population have a certain disease and 99% are free from the disease. A test is used to detect the disease. The test is positive in 95% of the people with the disease and also falsely positive in 2% of the people free from the disease. If a person selected at random from this population has tested positive, what is the probability that he or she has the disease? All right, so the first part of this tree is going to be disease, no disease. Now, this was my choice of lettering. You don't have to use exact same lettering here. My choice of lettering was I just went positive, P for positive and N for negative. But you could use a P and a P prime or something if you wanted to. Whatever makes you happy there. We just need the right numbers in the right position so we can multiply the correct values together. So that was just my choice here or whatever. So now let's see how the tree panned out here. Defective, not defective. Let's go back up here. 1% have it, 99% do not. So 1% defective, 99% not defective. The test is positive in 95% of the people with the disease. So the probability that it's positive given that you had the disease, in other words, positive given that it came from the disease, is 95%. So even though a small probability to have the disease, it's, you'd want a high probability that it tested positive. And then down here, 2% are tested positive that did not have the disease. So you were tested positive, 2% chance given from the fact you did not have the disease. Now, these other two numbers were kind of what I used to explain that last problem. Just you can fill them out to make them add up to 1 on those trees. So let's see what this question's actually asking. What is the probability that has the disease if a person is selected at random. So they are asking disease given positive. D given P. Now, I believe I mentioned this last week in the conditional probabilities is, you have to be careful the way they word these sentences sometimes, even for the kind we were doing last week and then also for this. Because sometimes they can start the sentence where they're asking the question, they can start the sentence off with saying, the probability part. Or they can put that part at the end of the sentence. So this sentence, or they can put the given part first, like they did here. If and given are the same thing. If they're positive, what's the probability that they have the disease? This could have been worded as, what is the probability that he, she has a disease if the person had tested positive? So it could have been either order. So you just have to pay attention. Whatever's following the probability part, that's the part that goes first in your conditional. That's your first part for sure. And then whatever's following either the word if or the word given, either one of those are fine. That's your second one. Now, I wrote the formula out, but we could do it without even using that formula. I just kind of wrote it out so you could see it. But we know that the P on the bottom, you get the P two ways, by D and by D prime. So you take 0.01 times 0.95 plus 0.99 times 0.02. That's going to be my bottom part. And then the top is just the D and the P multiplied together, because that's what the question's asking. But if it would ask D prime given P, these two would have been the numerator. So 0.01 times 0.95 is the numerator right here. There's all the stuff that makes the denominator. And we just divide those numbers and we get 0.3242. All right. So the probability of having a disease given tested positive is 0.3242. Because you can still test positive and not have the disease. All right. All righty. Isn't this fun? Beautiful. I forgot to bring up, okay. Let's bring up some homework here. Let's log into our Pearson. Okay. All right, where are you, Pearson? I have you right there in that Pearson. Oh. Let's do my math lab. So let's try a couple out of here and see what we got going on. Okie doke. I'd like to thank Mr. Swain for the reminder. Sent me a message there about what I said last week, mistakenly thinking that this was spring break week. So I'm glad we got that all straightened out. It is definitely next week. I'm sure a lot of you probably realize that, and just if I'd have shown up, then the joke would have been, it wouldn't have been a joke on me. I wouldn't have been the other way around. I wouldn't want to miss it. I probably would have figured it out at some point, but I was glad he told me. Okay. Okay, let's see what we got here. I guess I should have made an announcement about the homework. I did a class last week, but See all the open stuff now. And, well, I'm surprised. It's been good. I haven't gotten any emails. I meant to make an announcement because nobody's free. They must have paid attention to what I said earlier in the semester, that there was no need to freak out about these homeworks being closed because they're coming back later. Usually I'll have a couple, 3 panicked people. So far, no one has. All right, let's see. There's 5 of these. I want to get to the more interesting ones. Oh, here's a disease one. Might come back to that one. Let me just look and see what else we got going on in here. That one looks like one I did last semester. I could try that one. Looks familiar. That one looks familiar too. Or maybe it's this one. I don't know how many, whatever, but yeah, that one looks really familiar too. And look at all the parts on these. We'll see. I want to do at least, at a minimum, 2 of them. But, maybe 3 if we're on a good pace here. Just kind of look at the number of parts there. Maybe it was the banking one that I did not do last semester. I don't know. Well, all right. I'll tell you what, I'll skip the disease one just because we just did a disease example. Nothing else wrong with it. Maybe I'll give this next one a whirl here. This one looked like fun. Trust in banking. Okay, here we go. This could be exciting. Okay. So we've got, let's see, 43% of banking customers have complete trust. 49% moderate trust, 8% minimal or no trust. All right, I'm going to come over to draw tree. This is where, the choice of lettering to label these is totally up to you. But I try to pick something, especially when I'm showing students. You can call it whatever you want, You could use A, B, C, D, whatever letters like that. But so this will be another 3 brancher here. I'm going to use C for complete trust. M for moderate, and the one that says minimal or no trust, I can't use M again. I'll just use N as in no trust. So I'll just use C, M, and N. And you use whatever you want, as long as you know what to put, what numbers there. You can put little emojis there if you wanted to. Who cares? But as long as you know what goes with what, that's all that matters in this. All right. And let's see. That was a 0.09. 43, 49, and 08. Sounds close, but is that right? Yeah, that was right. That's a miracle. 43, 49, 08. Now let's see what's branching off of these. Of the bankers that have complete trust, 68% are likely to recommend their financial institution. So in other words, that tells you of the banking code, so it's coming from the complete trust. That's why I knew those 3 were first in the tree. Oh, I don't know. Very likely to recommend. I'm just trying to think of what I want to use. I'm going to use R and R prime. I don't know. I'm going to use R for recommend. Like I said, the good news is it makes no difference. 68%. So I'm gonna go R, and but I just figured I don't want to write them out to save time. I figure if I just, since I'm saying them orally here, you'll be okay. If you need to ask me, just ask me. But maybe the more proper way would be to write them all down. You know, C is for this, M is for that. But you're smart people. I'm sure that you're that's okay. But if I need to say it again, that's okay. But I don't think you need me to write it. So that was a 68. Let me get 2 for 1 here in this next one. Moderate trust, 23% will recommend. And for no trust, 3%. So next one will be 23 and 3. Now, I don't know if we need the not recommends or not, but I'm going to go ahead and just put those numbers in there. But, you could always wait and see if the question it's asking needs it or not, and you could decide whether you want to. That'll be point. Just go 1 minus each of those. Don't get cocky like me and do it in your head. Watch me do one wrong here in a minute. Yeah. The last one's kind of interesting, not so much for the Bayes theorem, but sometimes I have people, 0.03, I'll ask them, okay, then what's the other one going to be? They'll go 0.07. No, not 0.07. That would be, 0.3 is 0.7, but 0.03 would be 0.97. So that's why maybe going with the calculator would probably be I guess it probably helps that I have like 1,000 years of experience working with numbers. So it's a little more familiarity for me. So. All righty. Compute the probability that a customer indicates very likely to recommend. The banking customer also has complete trust. Okay. We've got to be careful on the labeling here. Now, recommend. Am I misreading? This question is worded kind of tricky. I'll make sure. Probability that complete trust given that they recommend. That's the only thing that makes sense. Unless are they just asking a number right off the tree? That would be kind of a waste of time. Because the wording's weird on this one. Indicates recommend. The banking customer also has complete. Oh, okay. This one's tricky. This one I think is going to be, it's actually going to be an and. Okay. I'm glad we're doing this one. Well, we'll see if I'm wrong or not. I think it's an and. I don't think it's a given. I think it's probability of C and R, which they may use this answer then to get to the next part. We'll see whatever the next part is. That's a little tricky, isn't it? See, I wouldn't have worded it that way. So what's the probability that they have complete trust and recommend? I would have used the word and. Yeah, I make sure my exam questions are never worded this tricky. I think it's those two. I should have already warmed up my calculator. Sorry about that. I'll just multiply that out without the calculator. Practice my in-head math here. In my brain math. 344. I used to be good at this. 344, 258, 258, 344, 258. All right, come on, wake up, fella. Where were we here? So it's 0.43 times 0.68. Oh, how do I have 8? Yeah, no, it's 2924. What was I thinking? Dang it. I got close, and I can't. And I missed the E. I should never miss the last digit because it's 3 times 8 is 24. Boo. Shame on me. Well, at least I didn't type it in there. Let's try 2924. I was just, 3 decimal places. 2924, so I'm going to go 292. It is Bayes theorem. Well, then, okay. Good news is we're going to need that calculation anyway. The wording is just terrible. I guess it's supposed to mean, all right, well, we can fix that. We need that anyway. I guess it's probability of C given R. But the way it's worded is strange. So that's going to be our top right there, though. I'll just put 2924. And that's going to be one of the ones on bottom. And now we go everything else that leads to R. Yeah, that was very poorly worded. 4923. Oh. And then what else? 0.08, 0.03. Well, so I'm just missing something in the question, but that didn't make it that clear to me. This is what it wanted. I got to use parentheses now. 0.2924 plus, I don't need parentheses here, 4923 plus, is it 0803? Yep. Let's try 718. Yeah, okay. The wording on that is just bizarre to me. Because the wording almost sounds like, what's the probability that you recommend given that you have complete trust? Which that would have just been, that would have been, like I said, recommend given complete trust. That would have been just that 0.68 number right there. That's the way the question sort of looked worded to me, but okay. Ugh, I don't like that. But now you saw how to do it, though, so. All right. Let's take a look at part B on this one. Okay, this one I'm pretty sure I know what it's asking. Here it's asking what's the probability is it just of recommend. It's the denominator of what we just did. So would have made sense if it would have asked that question first, actually. Because this is probability of R on the bottom. All this. So all I got to do is put that in the calculator. And, all right, so what if I take, I'm trying to take my calculator, so I got 2924 divided by all of this, I could do the reciprocal of this. I'm just trying to get away with that. I'm going to multiply all that again. And then multiply it by 2924. Let's see if this is wrong. I'll do it the proper way. But it's that bottom row of numbers. Not 7175, because that 7175 is including that numerator from the other part. I'm sitting there pointing at the calculator with my finger and nobody can see that. Oh, wait. Oh, good Lord. All right. Times. If this doesn't, I'll probably just go back and multiply them all out again. And so it's 3 decimal places. I'm going to go 210. If it's wrong, then I'll multiply it out properly. Oh. All right, so let me multiply it properly. So something, my little trick there probably did not work. But it is telling me, you see that what it's showing there. I was right about the concept. It's the denominator. So whatever little trickery I did there did not work. So I'm going to go back to the 2924 plus 4923 So obviously I got part A right, so I was using the right numbers, but whatever little trickery I tried there, it didn't work. And then 0.08, 0.3. All right, let's try 408. Okay, some of the little tricky stuff there was no good. I'll probably do another one of these before we go on break. I might not have time to do all 3 of those. I'll just look at these next 2, and they're both fine as far as I recall, but maybe this one has more parts. If that sounds more exciting, you want to do one that has more stuff to it. Okay. So this will look more. We'll do this one. We'll give this one a whirl. The one before is fine too. I mean, let me see if there's anything special about it really that I wanted to mention or whatever. I remember doing this one last semester. Now I'm kind of intrigued. But this one's actually whether the company's bidding for the job or not bidding for the job, and then whether they actually get the job based on the bid. It wasn't that bad. Okay. That I can recall. Well, let's go to this next one. Textbook. So, this one's got 4 branches on the first go around. Yikes. Well, okay. Just more tedious. Yeah, I remember this one now. Huge successes, modest successes, break even, losers. So I'm going to use H, M, B, and L. All righty. Break even, loser. Sure, this will only be 2 here. I don't know what they are yet, but I'll figure those out. See what that is. I'll get those first 4 here real quick. Those will all be given. All right, let's see. 20, 30, 30, 20. I can remember that. 20, 30, 30, 20. Okay, there's branch 1. And let's see what the other part of this is asking. Favorable, not favorable reviews. So I'll just use F for favorable, and I'll use F prime for not favorable. Okay. Yeah, okay. Oop, I meant to change the color there. That's okay. I believe that one was 90, 96, if I recall. I'll double check that. In other words, it's saying the probability it got a favorable review if it was a huge success was 96%. That kind of makes sense, doesn't it? If it's a huge success, you would probably think it would get a favorable, highly favorable review. 70% of the moderates received that. So 70, and then 50% of the break-evens receive favorable, and 20% of the losers receive favorable. So it's 0.7, 0.5, 0.2 for the next 3. .2 or 0.3? Yeah, 0.2. Now, I don't know if we'll need these, but it doesn't take me that long to do them. I'll do the, the not favorables here. So that'll be 0.04. That'll be 0.3. That'll be 0.5. That'll be 0.8. Yeah, I don't know if the question is going to ask that or not, but they're there if we need them. So just a little extra multiplying on these problems, it looks like. Let's see what the question's asking. All right, probability that if the book receives a favorable review, the book will be a huge success. So it's huge success given favorable. All right. Okay, I'm just going to skip the formula part of this. Go right to this. Okay. So huge success favorable on the top is going to be 0.2 times 0.96. I'll just put that problem on the bottom. Plus, oh, I made it 2 now. Okay, let's see what we got. Everything that goes to favorable. 0.3, 0.7. 0.3, 0.5. And then 0.2, 0.2. All righty. So let's calculator time here. So 0.2 times 0.96, I believe, yeah. .2 times 0.96. I'm going to do these separate because usually I just do it in one string. But in case I have to use this denominator again in another part, I would like to know what its answer is by itself, because whatever I did a few minutes ago, I did not get the number back correctly. So let me just do this string out right here, and then I'll just, it makes a little extra work, but it might save us for the other parts of the problems. What are they? Let's see. 373522. Let's see if I can remember that. 373522. 373522. Okay, I wasn't talking there, so I could remember those numbers. So now let me take 0.1992 divided by 592. So let's see if doing it that way is going to help us in any of the other parts of this problem. And how many decimals does it want? 3. So about 324. Fantastic. Look at us go. Favorable review will be a modest success. So modest given, okay, I'm really glad I did it that way now. We'll do this real quick. Modest given favorable. What was that number, 592, whatever it was? Yeah, 592 is going on the bottom again because it's still the same probability of the favorables here. So all we need is the two modest numbers, 0.3 and 0.7. I believe that's the modest right there. I'll double check that up on the tree, but yes, 0.3 to 0.7. Yeah, so I'll do this in one step. So that's going to be 0.21 divided by 0.592. Let's try 355. Woohoo! Look at us go. Oh, it's consistent here, isn't it? So it's favorable, break even. So it's going to do it probably for all four of these. That'll be quick and easy without already having that denominator. So the probability of, so hopefully you'll be able to use this little time-saving technique when you get to this problem. So that'll be 0.3 and 0.5. Oh, I already multiplied it out in my head. That's going to be 0.15. So it's 0.15. Once again, you might not, don't do it in your head just because I am. 0.15 divided by 0.592. Let's try 253. All right. And I saw that one coming. Loser given favorable review. Be 0.2 over 592. And 0.2 times 0.2 is 0.04, not 0.4, 0.04. Once again, you don't do that yourself. Zero 0.68. Hooray for us. What proportion of textbooks receive favorable reviews? Well, guess what that's going to be? That's going to be that 0.592 answer we keep using for every problem. That's going to be the denominator because that's the probability of favorable. On the bottom is that 0.592. So we just type this in here. Beautiful. We got it. Company bidding on a shopping center. The banking problem looks interesting. I don't know. Let's see. I think I'll do this one if that's okay with you. So let me just kind of snip this problem out. One part, I guess that's probably got another. All right. Let's snip this out, and I'll go to my scratch page and work this out for you. All right. Okay, construction company A should have submitted a bid for a job, and its main competitor, company B, has submitted bids 70% of the time. Company B does not bid on the job. The probability that company A will get a job is 20%. If B bids on the job, the probability that A will get the job is 0.15. Okay. All right, so it looks like kind of a weird sort of looking path here. You know, I first looked at this problem, I'd assume, you know, when you see a company A and a company B, you think they're going to be the ones that are sort of side by side here on this tree. But that's not what we're looking at in this problem. It's like B, you know, the A is dependent upon B, in other words, what B does. So I'm thinking we're going to have, let's define B, company B bids on job. And A will be company A gets the job. All right, so I'm doing this one for the first time. Hopefully I won't mess this up. So if you think something, those other ones already worked out last night, so I knew those were okay. So by all means, if you think you see something you don't like here, chime in there. So I'm going to go like this path right here. I'm just do a B and a not B. Then I think we have an A and a not A. I need to, let me copy all this, or I didn't realize I was at the end of a page here. I guess, well, I can just drop the tree down, I guess, to the next page and leave everything else where it was. And we just scroll back up there, well, I can just bring this down so we kind of don't, so I don't scroll back as far. Yeah, I should have looked where I was on the page. And I would have put this on a new page, obviously. I think that'll work. And then we need an A, not A here. With, you know, A prime meaning they did not get the job. Okay, so company B submits bids 70% of the time. There's your 0.7. Now we can come back and get that B prime, which I will. All right, I'm just going to keep everything in red ink right now, and I'll switch. But, you know, on a 2-branch tree, like I said, if you know one number, the second number means it has to add up to 1. So let's see what, if the company does not bid on the job, so we're going the B prime route, the probability that company A will get the job is 0.2. So the probability of A getting the job coming from B not bidding, that would be 0.2, would be right there. So obviously they've got to give me a number for that top part. If company B bids on the job, the probability that company A will get the job is 0.5, 0.15. This one, okay. No, it's fine. All right, okay. So I'll go ahead and fill the rest of this out in case we need any. We might need these, I don't know. But this we might not. But this would be a 0.3. This would be a 0.85. And this would be a 0.8 to make them all add up to 1. So I don't know if we'll even need those. So let me carefully read the question. If company A gets the job, what's the probability that company B did not bid? Did not bid. So that is going to look like this. P of B prime, let me just double check that. Not bid given that A got the job. So once again, you see how these questions are always, the first one in terms of the second one? That's why they have to be used. You have to use the Bayes formula. Okay, so let's see what we got. We're going to have P of B prime times P of A given B prime. Now everything that leads to A on the bottom. P of, okay, same thing. Well, I can do B for, yeah, the order doesn't matter here on this. So I'll do the P of B just because it's at the top of my tree. But what I said earlier was, though, whatever you have in the numerator is always going to be one of the terms in the bottom. It didn't have to be first, but it will always be in there as one of in the mix. Yeah, so it's okay. I didn't have to put it first. So actually, I'll circle this to show you that we did have to calculating that number was important, but everything else we had. So we did have to figure that out, but that wasn't hard. So we did need a missing number there. All right, so let's see what we have here. B prime, 0.3. A given B prime is 0.2. And P of B is 0.7. And then probability of A given B is 0.15. And then I know that one on top is going to be there on the bottom. All right, so let's calculate this. I probably would try to avoid, I think I would try to do it one step if possible to avoid too much rounding in the denominator and stuff, because it mainly just for a test it wouldn't matter, but because you'd be close enough to the right answer, but you know how my math lab can be kind of picky at times. So 0.7 times 0.15. So I would try to do it all in one step just for accuracy. But that's okay. You probably, you might not need to do it, but let's just, this one you probably wouldn't, because it wouldn't have that many decimal places. But if you did do it separately, just make sure you use enough decimal places for what's on the bottom, because when it divides, that's going to affect it a little bit. So 36, 36, 36, 36. Now, what does it want? 3 decimal places. So 3636 would be 0.364. All right, here we go. Come on, give me a fantastic. Fantastic. Got it. I'm assuming you probably don't yell at these when you do it, right? So I don't know. what is the probability that just company A will get the job? That's kind of an odd question. Not a bad question. That's kind of an odd question, but I don't really see the point of asking that. But actually, that's the denominator. So I don't know why they're asking just for this. So this is the probability of A is all the stuff that leads to A on the bottom. So it's just the bottom part. That's why I don't see the point in asking that, but that's okay. I'll humor them here. So I'm just going to do the 0.7 times 0.15. I guess to me it would have made more sense if they would have asked this question first, and that's what's weird to me. And then if they would have asked what we just answered, that order would have made more sense. So I'm going to go 0.165, unless I'm not reading something right here. We'll find out, won't we? Bam! That was it. Okay, so I just thought that was kind of odd. Bum, bum, bum. All right, this will be the last section for chapter 4. Okay, I have this all up and ready. Let's go back to the notes. Okay, this section's not too bad. It's interesting because this section has the most homework problems, but a lot of them are just like quick. You just plow right through them, no multi-parts or anything like that. I think there's like 12 of them, but you'll see we'll do some of them. You go through them and it's just super quick. They don't require near as much thought process as the Bayes theorem does. Counting rules. All right, we're going to learn how to count today. Isn't that exciting? Some of this stuff you've probably seen in the Math 1305. I'm not sure why they brought it back up again, but it's all right. I just go with whatever they tell me to teach. So, all right. So if you're counting K mutually exclusive and collectively exhaustive events that occur, can each number of n trials, the number of outcomes is equal to K to the n. Meaning that, here's a good example, and I've got some other examples, but if you flip a coin 5 times, and you have 2 options, heads or tails, sometimes people will mistake and think, oh, I mean, how many different outcomes are possible? Like head, 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 tail, tail, head, tail, tail, all that. They might go, oh, it's 2 times 5 equals 10. No, it's not multiplication, it's exponential, it's 2 to the 5th, but obviously exponential is repeated multiplication. So it's 2 times 2 times 2 times 2 times 2, and 32. For example, if you took a 6-sided die and you rolled it 3 times, all the different outcomes you could get would be 6 to the 3, which is 6 times 6 times 6, which is 216. Oh, should be little dots there, sorry. There we go. And, okay, not too bad. This says how many 5-digit zip codes 0 through 9 are possible if each number may be repeated. 0 through 9 actually is 10 digits, so don't let that trick you. You can count them up if you don't believe me. 0 through 9 is actually 10 numbers. So if they can repeat, it would just be 10 to the 5th power, 10 times 10 times 10 times 10, 100,000 different possibilities. How many 5-letter codes are possible from the first 7 letters of the alphabet if each letter can be repeated? It's a little tricky there with the 5 letters and 7 letters. The 5 just means how many times these are going to be multiplied together, because the entire thing is the code. In other words, AB, ABA could be a code or something like that. So there's the first 7 letters of the alphabet, all 7, and then you can have all 7 again. So it's 7 to the 5th power, and that ends up being 16807. Now, the second counting rule is a more general version of the first rule, except it's allowing for a different number of possible events to can differ from trial to trial. So it's also a multiplication type of rule, except it's not an exponent kind of rule. You just multiply the number of each possible outcomes together. Let's say you were trying to combine a coin flip with a single die roll. In other words, so like H1 would be an outcome, or T3, tail followed by 3, that would be an outcome. What you would do there is you would take the fact that the heads and tails has 2 outcomes, that makes 12. 2, and then times 6 for the dice, that would give you 12. So 2 times 6 would be 12. And you could list those out for that one because they're so small, you'll see that it was right. Now, here's a certain type serves a sandwich, if you're going to get a meat sandwich or not, whatever. But just for this example, just kind of go with it here. Let's say we got 3 kinds of bread, 5 kinds of meat, and lettuce or sprouts. So be careful there because it's not using a number, but lettuce or sprouts implies 2 choices. So just watch for that. So then how many different sandwiches, assuming you can only take 1 item from each one, only 1 from each. So that would just be 3 times 5 times 2, 30 possible sandwiches. Isn't that exciting? Now, license plates. Let's suppose a license plate has 3 letters followed by 3 numbers. How many combinations are possible with and without repeats? Let's look at with. 26 letters, first one. 26 letters, the next one. And then 26, the next one. Then you go over to the digits, the 10 digits. So you go 10, 10, 10. So you multiply those to get numbers together. And you get over 17 million. Now here's what happens if you're saying they can't repeat. You'd have all 26 available for you on the first one, but then whichever one that you use, the first one cannot be used again, so it's gone. So you only have 25 choices on the next one. And then when that one's used, the first 2 can't be used again, so then you got 24. Now you start fresh with the digits. You've got all 10 digits, but whatever digit is used there can't be used the next time, which is 9. So either the first 2 can't be used again, so there would be 8. So you multiply those 6 numbers together. And you get a little over 11 million possibilities. All right. Okay, this one's a little more challenging. We like a good little challenge here, don't we? Access code consists of a letter followed by 4 digits. Any letter can be used. The first digit cannot be a 0, and the last digit must be even. So it says nothing about really repeats or anything. So don't, you never want to throw stuff in there you don't actually see. So it's not a matter of repeats or not. So let's kind of look at this position by position. Okay, the first one's easy. Any letter can be used, all 26. Now, the first digit cannot be a 0. I mean, it can be anything 1 through 9. So there's 9 choices there. Next one, no restrictions here. Any of the 10 digits can be used, no problem. Same thing with the next position. There's no restrictions there. The next restriction is not until the very last digit. Must be even. So if it must be even from 0 to 9, 0 is not an even number, by the way. 2, 4, 6, and 8 are your only choices. There's only 4 choices. So you would multiply those 5 numbers together and get that answer. Okay. Now we're going back to the zip code problem we did earlier, except now we're saying no repeats. So instead of 10 times 10 times 10 times 10 times 10, whatever, you lose one each time. So it's 10 times 9 times 8 times 7 times 6. We know to stop here because we're only looking for a 5-digit code. So that's where you would stop the multiplications, however many. So each number represents a digit. And you multiply those together, you get 30,240. All right, we're going to learn about factorials here. I kind of need that for permutations and combinations. All righty, let's see. A number of ways items can be arranged in order. This exclamation point means factorial, and it means you take that n, you multiply it by n minus 1, you go all the way down to 1. Now, 1 factorial is also 1. 0 factorial is also 1. Because it seemed like it might be 0, but it's not. So like it's like one way to choose nothing, basically. There's one way you can do that. Another way to look at it, that's okay. But 0 factorial is clearly defined as 1. The calculator, I'll show you where the calculator is in the TI here in a second. Now I did it the long way, but I'll show you. You would want to use the factorial key. So how many ways can 5 paintings be arranged on the wall? So every time you put them up, you know, that's a different order. It's not like just putting them all up there in one time and that's it. So each position you put them in is a different order. Okay. So if there's 5 paintings, it will be 5 factorial, which is 5 times 4 times 3 times 2 times 1 is 120. Like I said, I'll show you where the factorial key is on the TI here in a minute. Even your basic scientific calculators will have a factorial key in there. Just have to kind of look for it. Sometimes they may have like X factorial instead of N. That's okay, same thing. How many ways can a batting lineup of 9 players on a baseball team be arranged? And these factorial numbers can get really, really large in a hurry. Let's see. So anyway, that would just be 9 factorial, 9, 8, 7, 6, 5, 4, 3, 2, 1. But let me show you what you do. Now, the way you do this is you have to put the number in first, whatever you're trying to factorial. You go to math, and on the older ones, they'll just say PRB. The other ones only have 4 of these, not 5 across the top. PRB, and you see it right down there, the 4th one, the exclamation. Enter. Now it knows 5 factorial. Enter. There you go. So for 9 factorial, we do the same thing. 9. Math. Factorial number 4, PRB, factorial number 4. There's the 362, 880. But these numbers can get massive in a hurry. Let's say let's just take a small classroom. Let's say a small classroom, and you have to do it a little differently. We're not worried about that, but if you're talking about empty seats, that's a little bit different story. But let's say there's exactly 24 students and 24 seats. How many different orders can 24 students sit in 24 seats? That's 24 factorial. Yeah, that's scientific notation, e to the 23. That means you start with that decimal where it is and you go 23 spaces to the right. So you see that it's showing 9 decimals. There would be 14 more zeros after that number. It's mind-boggling. How could it be that many combinations of 24 students and 24 seats? But it is. It's mind-boggling how large these numbers can get. I think the calculator blows up. Well, I don't want to blow up, but I think 69 factorial is the largest one it can handle. Because the calculator can only go to the 99th power exponential-wise. Anything over that, I believe it's 69. I'll check here. 69 should work, and then 70 should give me some sort of overflow problem or something like that. I'm not really going to blow it up or anything, but just to show you. Well, we're not going to have to worry about anything like this, but yeah. The next one, multiply it by one more number. I believe that's what's going to kick it over too far, 70. Oops. We blew its brains out. Ha. Cannot do it for that large, so, but that's not going to be a problem for you, so don't worry about it. But yeah, it's takes a little more powerful type of computer thing to handle that. There was a calculator, it's not really around anymore, but a long time ago, 20 years ago, maybe used a little more recently than that. It was TI-86. And it was more for engineering and science. I think it could do actually higher factorials. But not since we started with the 82s, 82, 83, 84. They have not been able to do anything higher than 69 factorial. All righty. Now here's where we're selecting maybe a different number of, it's not a full set of rearranging an order. We're selecting a subset out of a group of people. Well, people, items, objects, people, whatever it may be. It's called a permutation. Now we'll talk about, there's going to be a difference here whether the order matters on this or the order does not matter. Permutation is going to be where the order matters. The order matters of the item. All right. We'll talk about different examples between order mattering and not mattering. So the number of ways of arranging X objects selected from 10 objects in order. And this permutation function, you don't have to use this formula because it's also in the TI. This command is right there where the factorial is. But here's the actual calculation. It's n factorial divided by n minus x factorial. Now we're going to look at things where the order would matter here. Horse race. The order that the horses finish matters. The numbers matter, what order they finish in. Based on how you bet. For example, let's say if you bet what's called a trifecta, and what that means is you have to predict first, second, and third place. Well, let's say you picked in this order. You picked 6 to win, number 1 to finish second, and number 3 to finish third. But it finished 3 first, 6 second, 1 and third. It was the right 3 horses, but it was in the wrong order, so you wouldn't win the bet. So that's why any kind of race like this order would matter. So if there's 10 horses and we're looking for how many possible 3-place finishes you could get, it would be this formula. Now I wrote 7 factorial, but the 7 comes from up here 10 minus 3. So it's 10 factorial over 10 minus 3 factorial. So it's 10 factorial over 7 factorial gives you 720. But I'll show you both ways here. I'll do it with the factorials. for people that are just using a scientific calculator. It doesn't have to be this one. But then I'll just show you the command that you can do this in one step. Well, let's show it both ways here. Ten factorial divided by 7. So I don't have to get the 10 factorial first. I can leave it sitting just like that, and then I do like that, and there's my 720. But the permutation command. Now, what you have to do is just like it was for the factorial, you have to put the first number in there, the 10. But now we're using two numbers, though. We weren't using two numbers before. The first number, then you go back up here to math, the PRB and the older calculators, PROB here, it's number 2, NPR. Number 2, you put NPR. Then you put the second number. Now, in the older calculators, it's just going to show NPR. The newer ones now do it fancy like this. Same thing, I promise you. If it shows 10 and it shows NPR 7, you're going to get the right answer. Don't worry about it. But so you put the first number, NPR, second number. Oh, excuse me. I did the wrong command. It's NPR, it's 3. Because the 3, it was 10 minus 3 makes it 7 factorial. Excuse me. So it's 10, choose 3. But doing this factorials, though, I did it right. But I made the wrong choice here. So it's 10, choose 3. That will give me 720 guaranteed. There we go. Okay. All right. Okie dokie. Here's another race one. Long distance foot race. How many different finishes among the first 5 places are possible if 50 people are running? So just using factorials, I'll write over here, it's 50 factorial over 50 minus 5. That's where I'm getting the 45 from. But don't do like I did the last one. I made a mistake. This time I'll do it right. I'll put 50, choose 5, just like I have it written correctly over here. But yes, 50, choose 5 is equal to 50 factorial divided by 45 factorial. But you can just do this straight up like this every time. You don't have to worry about that. Ooh, that's kind of rude, isn't it? There's 254 million ways, and more than that, to list out the top 5 finishers in a 50-person race. I would not want to have that job of having to list those out. I can't imagine how long that would take. Might take a couple of lifetimes. I don't know. All right. So anything, now we've done order with horse racing, but here's another one where this is considered order and ranking or anything. So we're choosing a president, a vice president, and a secretary is chosen from a committee of 7 people. I mean, yes, we're choosing 3 people, but they each have specific functions. Specific, the president's probably higher than the vice president and so forth and so on. If it just says how many, that'll be the next thing we're going to learn here in a minute. If it just would have said, how many ways can you just choose 3 people out of 7 at random? Just without regard to any kind of order. That'll be the next thing we're going to learn. But this is order specific because each position is ranked. Okay. So it's a permutation. Oh, here's some of these. Okay. Yeah, I even got the old calculator. I've got both calculator displays down there, don't I? Yeah, those I was talking about. There's what it looks like under the old one. And here's what it looked like with what I was doing now. Still get the same right answer, so it doesn't really matter. They just decided to make it this fancy little subscript form there, which is sort of what the formula looks like, but who cares? So it's, I won't even redo this one, but 7 choose 3. There it is right there, 210. I wrote it out via formula, but you don't have to do that. I've seen problems like this where it was president, vice president, secretary, and treasurer. So it'd be 4 people. So just, if you see one like this, just don't automatically lock in 3 in your brain without reading it completely to see if there's a 4th position there. I've had people make that mistake before. Counting rule 5, combinations. This is where you're selecting X objects out of N objects, irrespective of order, meaning the order doesn't matter. Whatever order makes no difference. So I can use several examples here, but I'll use the horse racing one. Suppose you're going to try to buy some horses or whatever. And let's say you want to buy the first 3 finishers in that race, just whatever 3 finished. Doesn't matter what order they're in, just the top 3. That would be calculated this way because you wouldn't care about the order. 6-1-2, 2-6-1, 6-1, 6-2-1. You're just selecting those 3. Or kind of like that committee example we just did. Suppose that it said we're just selecting 3 people out of 7 just to form a committee. There was no ranking of the positions. That would be what's called a combination. So anything that doesn't imply order matters. It's this formula. Now the combination answer will always be smaller than the permutation answer because you're not taking order into play here. So like using that horse thing, once you choose like horse 6, 2, and 1, they've been chosen. They don't have to be counted multiple ways, in other words. Like 6-1-2, 1-6-2. Once those 3 are picked, they're gone. So the only difference between this formula and the other formula, once again, most of you probably aren't going to need the formula because this is also on the calculator. It just has a little X factorial on the bottom there. That's the difference. Which, since you're now making the denominator a little bit larger, that makes the value overall smaller. So like I said, the combination will always just pick any 2 numbers. I'll show you. The permutation answer is always greater than the combination answer. Okay. So here's telling you, conceptually speaking, order is vital, important for permutation, and combination order is irrelevant. Makes no difference. So here it says how many people, 4 people can be chosen from a committee of 12. Now I've got it written out in factorials, and then notice I've got parentheses around those 2 on the bottom. If you're doing it that way, it's very important that you keep it in parentheses because you want to make sure they're being multiplied together first on the bottom, then you divide. But in the TI here, doesn't matter. You just got to choose the right function. 12. So if we're just choosing PRB, and it's number 3, so it's the one right below the NPR and CR. So easy to find. 4. And 495 ways. So once you choose 4 out of that, they've been chosen once. There's no order ranking of those 4 people. That's it. But now let me use that example. I'll just use this one verbally here. Now suppose it was going to be just a committee where it was a president, vice president, treasurer, or secretary. Then that would be 1, 2, 12, math, permutation. because once again, that's same as before, the ranking of the positions. And this is going to be a larger number. Like I said, every time a permutation produces a larger result than a combination. There you go. 11,880. All right. How many 5-card hands are in a 52-card deck? That's a combination because the order does not matter, and you don't have to be a card wizard. But let me write down an example. I won't worry about writing suits or anything like that. But it's not the order that you visually are looking at them. Let's say, and once again, you don't have to be a card wizard here, but combinations they're not. Let's say I'm looking at these cards here: ace, ace. I don't know, king, 3, 7, or whether it's ace, king, 3, 7, ace. In other words, the way you're looking at them doesn't matter in a like a poker game or something like that, or like if I was playing video poker in a machine. That's like I like to do when I'm in Las Vegas. That's going to count as a pair of aces. It didn't matter what order they were presented to you visually. That's a pair of aces. Anything you do if you were just like holding a deck of cards and moving them around, that's not really changing the value of it. It doesn't make any difference. So that's why, so these card problems are not order specific. Now, somebody wanted to, design some weird complex problem where it was, that's different, but we're not going to do that. So that's ridiculous. But so it's just not, so it's 52, choose 5. So 52. So what I wrote on that other page with those 2 sets of cards, that's not 2 different orderings. It's not, that's not, those were both the same thing. 2,598,960. So 2,598,960. Okay. We're not getting, it won't be fun to get a little more farther into this, but we're not going to. So I'm just going by what they had there, because, probably did more in this than in finite math. You probably know a lot of this already, so that's good if you do. That's fine. A shipment of 30 calculators is shipped to a high school. 4 of these calculators are designated for Mr. Fred's calculus class. How many selections can be made? No order. So there's just 4 defective ones floating around there, so 4 defectives. So you just choose, which they have they're not order specific. So it'd be 30, choose 4. And that's going to be 27,405. Okay. Oh, hit the enter twice there. Sorry about that. There it is. And that looks like, for content-wise, that's it. So let's just try a little bit of the homework, and then we can call it a spring break here. How does that sound? I'll take that as good news. There's no point in starting the next section today. We can certainly wait till after spring break. Not that eager to jump in there. This will be perfect. Like I said, this one I was talking about has like 12 problems, but they're all pretty quick. I could probably do most of these here. Maybe I'll do all of them real quick. Let's see. 9 multiple choice questions on the exam, each having 3 answers. How many different sequences of answers are there? Okay. So we're starting out with those multiplication problems. So basically you got 3 choices in the first one. You got 3 on the second one, 3 on the third one. That's going to happen 9 times. So how about 3 raised to the 9th power? How does that sound? That would just be 3 times 3 times 3 times itself 9 times. $19,683. Type a whole number. That's kind of funny because the answer's it's got to be a whole number. So there'd be no reason to be typing anything that wasn't a whole number. Yeah, we're not getting into the, unfortunately, we went a little further. We're doing these counting rules, but I like the ones where it actually starts getting into a little bit of probabilities, like let's say, we're not going to do it. Here's what I'm talking about. Let's say you've got a group of people. Let's say you have 7 women and 5 men. What's the probability that if you choose 7 at random, you choose 4 women and 3 men? You might have done that in finite or whatever they call it now, but we're not going we didn't quite get into that in this class, but those are fun, but that's okay. We're just learning how to do the counting part, not the probability part. Oh, it's got 3 parts here. What do we got here? 10 positions, bank vault. How many different dial combinations are there? How about 10 times 10 times 10? I think it's 1,000. Wonderful. What is the probability that you open that bank vault one try? Well, of course, this assumes the obvious is only one right combination. Okay. It would just be 1 out of 1,000. I can make this a decimal, but it says I can put an integer. Well, that's stupid. It should have said decimal or a fraction. Probabilities are going to, well, I mean, the only integers a probability answer could ever be is either 0 or 1 or something in between that, but I find that oddly worded there. But I could have seen putting in a decimal, which is 0.001. Now, why is their task is why is this not done by the method using combinations? Any kind of problem where it can repeat. If it can repeat, it's not either a combination or permutation. If you can repeat, so this could repeat, so it completely eliminates the idea of combination or permutation. Well, I'm not so concerned about the order matters part here in C as I am concerned about each number can occur more than once. That's the key that makes it not be that. That was those first rules we learned, which I usually call them multiplication principles. I don't know what they were called in this book. I don't remember, but okay. That's the reason why. Coin is tossed 9 times. How many outcomes are possible? Well, there's 2 outcomes on each coin, 9 times. How about 2 to the 9th? That sound good? $5.12. Yay. 4-sided die. 4-sided die. That's kind of weird. Well, okay, but at least it told us that. They have some of those games where I don't really play them, but some of those things like Dungeons and Dragons and some of those kind of games, sci-fi games, where you've got die that are like 20-sided or something like that, whatever. So they have like little flat spots on them where they can land in a bunch of different positions. But obviously, if it's not a standard 6-sided die, it better tell you, like this one did. It told us how many. 2, 6, 2, 1, 4, 4. If it's just a regular die, it'll be 6, but it better tell us if it's not. 2, 6, 2, 1, 4, 4. All right, discuss your differences to answers A and B. This is kind of tricky. Mutually exclusive. Outcomes. Collectively exhaustive means they can both, they're going to contain, the complement's going to contain everything in the set, but they're not. How would A, I'm looking at answer B, not, but I'm trying to figure out what's the difference between B and A. A has H and T, 2 outcomes. D has, 4-sided. We'll say 1, 2, 3, 4. They're similar ideas. I'm trying to figure out these answers C and D where they're giving different. I don't see what would make it different between the two. I would think they would have the same results. I'm going to go with A. A, because it's telling you. Okay. Yeah, there's 2 mutually exclusive heads, tails on the first one. But yeah, they need to work together because I knew that they weren't going to be, different. They're both mutually exclusive. And they're both collectively exhaustive. All right, well, whatever. Okay. Women's jeans. 6 sizes, 4 colors, 2 different styles. How many do you need to have 1 of each type? How about 6 times 4 times 2? I don't need a calculator for that. I'm going to go 48. Woohoo! Build your own burger. Ooh, now I might need a calculator. Maybe I don't. 8 breads, 4 cheeses, 3 cold toppings, 3 different sauces, 1 from each. 8, 4, 3, 3. I'm going to try to do this in my head so you can laugh at me wrong. I think it's 288. Woohoo! But it was 8 times 4 times 3 times 3. Yeah, I thought I at least would say that verbally since I didn't put it in the calculator. So 8, 4, 3, 3. I said, you should not try that experiment at home. You should multiply it in the calculator. Okay. 12 teams, different orders of finish possible for the first 3 positions. Okay, it's going to be a permutation because the order is going to matter here. Who finishes first, second, or third out of those 3 teams. So it should be a permutation problem. It should be 12, choose 3. Yeah, this one I will not do in my head. 12, math. NPR, 3, let's see how that looks. 1,320. Yay! You see what I mean about how this section is so quick to go through here? 13 rows in a vegetable garden, 13 vegetables. Each vegetable will be allowed in 1 row. $13. Yeah, one thing about permutations that I mentioned earlier, if you say like anytime that the two numbers are the same, like 13p13, that's always just the same thing as saying factorial. So I think it's just going to be 13. I'll show you that in the calculator. I think it should just be 13 factorial whenever the items are all the same, but I'll show you that just to so you can see that I didn't just make that up. But you can still do it as a permutation of 13, choose 13. If this ends up being the right answer. Unless I'm misreading the problem. 13. $13. And for combinations, if the number is the same, the answer is 1. So let's try this. 62270. Oh, forgot to. The last 5 digits are 20800. Yay! Big number? So there we go. Well, she wouldn't have to consider all possible outcomes there, but maybe certain vegetables don't play nice with each other, so you have to keep them separated, and I don't think that's true, but all righty. How many ways can a senior project manager and associate project manager selected if there are 13 data scientists? Okay. Senior project, associate project, different rankings. That's 2 people. So there's your number 2. And the order matters. So I think it's going to be 13P2. Because the fact that they're ranked, is $156. Excellent. 6 members of a group of 9 are to be selected to a team. How many ways are there to select these 6 members? Okay, there's nothing in there that indicates that the order or ranking or anything between them is going to matter. So that means it'll be a combination problem. We're just taking 6 out of 9. How many ways can I get 6 out of 9? Without regard to any kind of order or anything like that. So I'm going to go 9. $84. I wouldn't be surprised if there were some of you that were following along with me and doing this in your section and just answering that. That wouldn't be a bad idea, would it? Answer them as I go there, Obviously, the Bayes one takes a little much more work there. You got to work them out more carefully based on your numbers. But 17 books to place in her backpack. There's only room for 14 books. Good grief. How big is this backpack if we can get 14 books in there? Or the books must be super thin or something. I don't know, but holy cow. All right. Nothing that indicates ranking here. So I think it's how many ways can you choose 14 out of 17? So NCR 680. Simplify your answer. I don't think I can get it much simpler than 680. All right. Look at that. Two more. I told you this. It's got a lot of problems, but it goes through quick. 4 winning numbers out of 50 without duplication. How many combinations of winning numbers are possible? Nothing indicating and that the order matters on these. And there's not any order. Except if you're the situation if you were doing like a Powerball, you got to get that one particular number right. But in general, the other numbers don't have to be in order. And thank goodness, because these jackpots would be really getting into obscene amounts if you had to get the numbers, not only get the numbers, but get them in order. Holy cow. They'd be getting into the billions all the time. So 50, choose 4. Now this one's not as challenging as our regular like Powerball, something like that. But even for this one, let me get the answer right first. Well, let me do this. Yeah, so this would be even more extreme for the Texas Powerball. I'll change this one to permutation just to show you. But the one with the C is going to be the right answer. Well, okay, so this is what it gets more extreme though, with choosing more numbers or whatever, but still only 4 is not that bad, but still, but yeah, let's see. So it's 230,300. All right, look at us go here. Nothing indicating order. They just want to take 4 of their bikes and display them. 4 out of 20 would be a combination. No order required. Okay. 48, 45. Check answer. Good job. We did it. We did them all. So that will officially conclude the program for tonight, but I'm sticking around to see if you might have any questions or anything you want to ask about, but